When you think of a physicist, you might think of someone standing in front of a blackboard, chalk dust on their pants, papers scrawled everywhere, and that might not be too far off a lot of the time. But sometimes, certain physicists need to leave the office and go to bizarre places to get the data they want. Today on our show, we are talking to two physicists who go to work in very extreme conditions, one at the South Pole and the other deep underground. We hear all about their day-to-day life and all of the weird things that they have to deal with, so stick around. You're listening to Why This Universe, a podcast where we break down the biggest ideas in physics. I'm Shalma Wegsman.
And I'm Dan Hooper. Most physicists do their work from pretty ordinary places. As a theorist, my work is pretty much confined to places like offices and meeting rooms, nothing out of the ordinary. And some physicists work in like laboratory facilities that might be on their university campuses somewhere, maybe at a national lab. And these scientists, at the end of the day, they get to go home and otherwise live pretty normal and ordinary lives. But there are certain kinds of research that can't be easily done from such accessible locations. And today on Why This Universe, we're going to talk to two physicists whose work has taken them to some pretty extreme environments. So we're going to start with Sasha Rahlin. Sasha is a research assistant professor in astronomy and astrophysics at the University of Chicago, the same department that I'm in, just down the hall from me. Her work is mostly on telescopes that are designed to study the cosmic microwave background. These include telescopes like SPIDER, the South Pole Telescope, and a future telescope known as CMB Stage 4. This work has taken her to the Amundsen Scott Station at the South Pole. Welcome, Sasha, to Why This Universe.
Thanks for having me.
Yeah, this is going to be fun. Let's just start by telling us a little bit about yourself, Sasha, and how you came to be the kind of scientist who studies the universe from the South Pole.
So I think I've always had an interest in astronomy and astrophysics. My grandfather was a rocket scientist with the Soviet space program, and my grandmother also worked with the Soviet space program. So when I was growing up, I always had passing interest in the stars and all that. At some point along the way, I thought I wanted to study like high energy physics, dark matter, that kind of thing. So as an undergrad, I worked with a dark matter group at MIT. But then when I got around to applying to grad schools, I ran into the person that would become my advisor, Bill Jones, who basically asked, "Hey, are you interested in building a telescope that's going to fly on a balloon around Antarctica? And we're going to study, the early universe, the Big Bang." And I thought, that's actually really cool. So yeah, I want to do that. So I went to grad school at Princeton University and I worked on SPIDER, and that launched on New Year's Day, 2015.
SPIDER was that balloon you were talking about.
Yeah. So it's designed to study the cosmic microwave background. I got to spend a few months working in Antarctica for that. So that's at McMurdo Station, which is the largest American station on the coast. In the summer season, it's about 1,000 people. So I got to live and work in that environment for about 3 months. And that was a really great experience. And I knew that I kind of wanted to stay in that area after I graduated. And I eventually got hired by the South Pole Telescope. And I have been going down to the South Pole to work on the South Pole Telescope pretty much every year since 2016.
Just to clarify to the listener who might not know the differentiation, so you talked about being at McMurdo, which is on the coast of Antarctica, but all these other trips you're talking about were at the actual South Pole, like in the middle of the continent. All right. Maximally remote.
Exactly. So it's a whole nother flight to get there. It's a completely different station. The nearest station to the South Pole is about 900 miles away.
So in a nutshell, what's so special about the South Pole? Like, there are obviously a lot of easier places you could build and operate a telescope from. Like, this must be, a lot of resources and a lot of money and energy and blah, blah, blah to do. Why there? What's so important about doing science at the South Pole as opposed to other locations?
Yeah, so the South Pole is actually a very unique site. It's arguably the best site for doing millimeter wave cosmology. The reason for that is that the atmosphere is very dry and very stable. So when we use a telescope that's sensitive to millimeter or microwave emission to look through our own atmosphere gets in the way. So we have to look beyond it. We have to look outside of that and all the way back to 13.7 billion years ago. And it's the water vapor in our atmosphere that makes it particularly opaque to millimeter waves. The South Pole is actually the highest, driest, coldest desert on Earth. The precipitous water vapor there is super low year round. And because the day-night cycle there is just one sunset in March and one sunrise in September, you don't get, daily temperature variations. You don't get daily weather really. So it's very slow moving atmospheric changes, which make it really nice to be able to subtract off that atmospheric contamination from what we're trying to see on the sky.
Cool. So I think at this point, let's bring in our other guest. We've got with us also on this episode, Dan Baxter. So Dan has worked on numerous experiments searching for evidence of dark matter particles, including Lux, Pico, and Domic. And these days he's working on quantum technology, superconducting qubits in an effort to search for dark matter. Dan and I met years ago when he was a postdoc at the University of Chicago. And after that, he became a staff scientist at Fermilab, co-leading its quantum cosmology group, which works on kind of the interface between particle astrophysics, like the stuff I work on, and quantum computing. Welcome, Dan.
Thanks for having me.
Yeah. So, just like Sasha did, can you tell us a little bit, about yourself and where, your interest in dark matter has taken you?
Yeah, absolutely. So I think my interest in dark matter doesn't come from a family history like Sasha's. My family, going way back, is all really educators and teachers. So I actually knew I wanted to be a teacher long before I knew I wanted to be a researcher. But as a kid, I really loved playing with Legos and things like that. And so from a very early age, I had the satisfaction of putting things together and solving problems. And it was in undergrad when I decided I wanted to try out some experimental research that I sort of realized that I really enjoyed it. And that sort of changed my career trajectory pretty significantly, because before that I was really planning, I think, on becoming a teacher like most of the other members of my family. And I realized that within academia I could still follow that passion, but also satisfy that urge that I had to solve problems and put things together. And so that's how I became an experimental physicist. I've worked on dark matter direct detection now for 12 years. And I think for this podcast in particular, the most relevant period of that would have been my PhD work, where I was working on the Pico bubble chambers, which are in particular deployed deep underground in SNOLAB in Sudbury, Ontario. So all of the experiments that Dan mentioned, and all dark matter direct detection experiments, are located deep underground because they are extremely sensitive particle detectors. And what that means is they are sensitive to anything that can deposit small amounts of energy in the detector. So that includes everything from cosmic rays hitting the Earth. The easiest way to get rid of cosmic rays is to go deep, deep underground, such that the Earth itself shields all those particles from your detector. And so what we do in the dark matter community is we go deep underground in order to shield our detectors from as many other particles that could create events as possible, so that we create a clean environment for dark matter to scatter in our detectors, which allows us to look for it. So when I was a grad student on the Pico bubble chamber experiment, I spent about 50% of my time for 9 months going back and forth to Canada, where I worked in the deep underground SNOLAB, which is 6,800 feet underground in an active nickel mine.
6,800 feet. Okay. So, what is that in miles or kilometers? Let's see. A little over a mile deep?
A little over a mile deep.
Okay. All right. That's really far underground.
And I think one thing that makes SNOLAB really unique out of all of the underground labs in the world, and there's a little under a dozen at this point, underground science labs, deep underground science labs. There's a few things that make it unique. One is that the entire lab is a clean room. This is very important because if you're going underground, you have to worry about mine dust, which has high levels of uranium and other radioactive isotopes. Not high in the sense that it would cause you health problems, but high in the sense that our detectors would measure it. Mm-hmm. And so we have to be very careful about protecting our detectors from all of the dirty environment down there. And so Snow Lab is, in particular, a clean room facility located deep underground. And I looked up a number here for this. The actual lab space in the clean room is almost 33,000 square feet. So that is an enormous footprint of clean laboratory space, 6,800 feet underground.
Wow. So maybe just for our listeners, paint a picture like, okay, so you're not living in the lab, right? You're living in some housing nearby. Describe, what it's like from when you wake up in the morning to how you get down to the lab and what conditions are like there.
Yeah, absolutely. So this is maybe the main thing that differentiates the work that Sasha just talked about from the work I talked about, which is that when you go to the South Pole, you're very disconnected from society because you're obviously in a very remote environment. When you're working deep underground, you still live, in a community on the surface, and you go underground for a day's work with the miners. And so that's the other unique thing about Snow Lab is of all of the mines in the world that have physics laboratories, it is one of the only ones that's still located in an active mine. So a lot of nickel comes out of the mine that Snow Lab is in. And so the first thing you do is you drive to the mining site. You change into your mine gear. Because in order to go into the mine, everyone has to essentially receive training from Canada to enter a hard rock mining area. So there was a time in the distant past where I was a certified Canadian hard rock miner. Okay. I'm still waiting for my certificate for that, but I took a lot of trainings for that.
Is it really called a hard rock miner? It sounds like
it is
bad play on music,
It sure does, and yep.
Heavy metal miner.
Heavy metal miner. Yeah, well, it depends on how you define nickel. I don't know. So you change into your mine gear, and then you walk from the Snow Lab surface facility to the elevator, or what we call the cage, which is what takes all of the scientists and the miners deep underground. And so at the Snow Lab facility, this cage is a 2-level mining elevator, where they pack roughly 30 people in per floor, like sardines. It has 3 walls, and the 4th wall is open. And so as they lower you over a mile underground in about 3 to 4 minutes, you see the rock flying past you, which is very exciting. And then eventually you get down to the 6,800 feet level, and the miners all wave goodbye to you because you get off there, and they continue on down to the deeper levels where they're still mining ore.
How long does it take to get from the top to 6,800 feet?
I forget the exact number, but I think it's about 3 to 4 minutes, depending on how fast they operate the elevator. So,
can you notice the pressure gradient?
Yes, actually, and this is a big factor for our experiments, because ambient pressure down there is about 5 psi higher.
Okay.
And so this is very relevant for doing science experiments underground, is that you have to actually account for the fact that if you calibrate things on the surface relative to ambient pressure, all of those calibrations will be wrong when you go underground, and so you have to be very careful with that.
Do things like your ears pop as you go down?
Oh, yes. Okay. Oh, you go very fast.
Yeah. All right. Wow. Okay.
Yeah. Your ears very much pop, and you shouldn't go underground if you have like a cold or something, because the pressure buildup can be very unpleasant.
All right. Okay, so now you're down there. You've gone 1,600 feet down. Now what happens?
So you wave goodbye to the miners, they continue on down further, and then you are just basically at the end of a mine shaft. And Snow Lab itself is actually located a 2-kilometer walk into the mine. And so you have to walk or trudge, really, 2 kilometers through the mine in your mining gear. It's very wet, it's very dark. And an interesting thing that surprises a lot of people is that it's very warm. You're deep underground, and so the rock actually has a lot of heat to it. When you look at the
geothermal energy, basically.
I think so. I don't know the exact physics of it, to be honest, but it's basically high 80s.
Okay, all right.
So it's quite warm. And so you walk 2 kilometers through the mine in your mining gear until you eventually reach Snow Lab. You basically turn a corner and then there's this entrance to the lab. Because the lab itself is a clean room and you just trudged 2 kilometers through a dirty mine, everyone and everything entering the lab itself has to be cleaned. And so all objects get placed in a room that is called the car wash, where they are manually hand cleaned before entering the lab. And all people go through some locker rooms where they essentially strip off their mine gear, shower, and change into freshly laundered clean room garb.
Okay.
And so after everyone has had a chance to shower off the sweat from walking through the mine and change into some clean gear, they exit the locker rooms and enter the underground kitchen, where we also have I believe, the deepest flushable toilets on Earth.
Okay.
And have a cup or two of what is objectively the worst coffee on Earth. Well, you don't care. Once you get down there, this is all very early. I forgot to mention the cage that takes you down in the morning is at 6 a.m. And so particularly if you're on a winter shift at Snow Lab, you go underground before the sun comes up.
Sure.
And then the cage up at the end of the day is at 4 p.m. And so frequently the sun has already gone down. And so similar to Sasha, if you're there at a certain time of year, you won't see the sun for days.
In that heat, the high 80s degree temperature that you said you experienced down there, that's year round? Does it matter if it's
year round? It's year round. And that's really surreal, actually, because, again, if you're doing a winter shift, the coldest it ever hit while I was stationed at Sudbury was minus 40, which is probably nothing to Sasha. But the temperature swing between walking out, because you have to walk outdoors to go between the two surface buildings. So you have to walk in your mine gear through what is minus 40 degree weather sometimes, get in the cage, go underground, and then sometimes it's 90 degrees.
Right.
And so the temperature swing that you have to experience over essentially 5 to 10 minutes is very intense.
Pretty intense.
What I will say is that a lot of people prepare for that by dressing for the walk through the mine, because that's 2 kilometers, whereas the walk between the surface buildings is about 100 seconds. And you know that because if it's minus 40 and you're walking through it, you really kind of think about it. And so most people, because they have to take off all their clothing underground anyways, don't wear that much under their mining gear. So that 100 seconds is pretty brutal. Because people dress for the warmth underground.
All right, let's use this as a good segue back to you, Sasha. Tell us about a day in the life of somebody doing science at the South Pole.
Yeah, it depends on the season very much. So there's basically 2 major seasons at the South Pole. There's the summer season, which is early November through mid-February. And that's when there's a lot of activity on station. That's when there's planes going in and out. And there's a lot of, summer maintenance kind of tasks that are happening on all the major projects. So SPT isn't the only science that's happening at the South Pole. So in the summer season, you're doing a lot of work.
How many total people are at the station in the Antarctic summer?
At peak, it's about 150 probably that they can house on the station. And sometimes it overflows, and they set up what's called summer camp. So it's a bunch of Jamesways, basically fancy tents that are heated and have like reinforced ribbing to keep them structurally sound. So once all that summer activity is done on February 15th, which is a very strict deadline, the last plane takes the last set of summer passengers out, and then you're left with the 40 or so people that you're wintering with. And there's no more passengers in or out. Sometimes there's a Baxter or a Twin Otter aircraft that passes through on their way home back to Canada. But that's your crew until mid-October, when after the winter passes and the temperatures get warm enough again to fly the bigger cargo craft down.
So you spend 8 months with your 39 closest friends in this close quarter environment. Yeah.
Oh, yeah.
Okay. Wild.
Yeah.
Now, everyone knows that Antarctica is cold, but can you give us an idea of some numbers here? Just how cold are we talking about here?
Yeah. So in the summer season, I believe the warmest it's gotten at the South Pole is maybe like in the single digits Fahrenheit. So
okay.
8 or 9 Fahrenheit, something like that.
That's the warmest it gets.
Yeah, that's the warmest. Yeah, and that's pretty uncommon. That's like let's call it a heat wave. Normally in the summer, I would say probably around Christmas, it'll be like minus 20.
Okay. All right.
I think last year on New Year's Eve, it was more like minus 40 Fahrenheit. Fahrenheit or Celsius. And in the winter time, so the reason, the station closes for winter is because around February 15th, the sun is low enough on the horizon that you don't get, the warming effect of the sun anymore to keep the air warm enough for fuel on the planes that we fly down there to stay warm. So that there's like a cutoff for when those planes can physically, land and take off safely. So after February 15th or so, the temperature starts to drop pretty quickly. And sunset is like March 21st or 22nd. And at that point, temperatures get down to minus 70 or 80 Fahrenheit pretty regularly. That's pretty common. And then sometime in the winter, often, we sometimes hope that this happens because it's an interesting, thing to have happen, but the temperature can get down to minus 100 or below.
Wow.
And there's a little bit of a magic number associated with that because, when the temperature is down at minus 100 or below for long enough, and it's particularly not so windy, we'll turn on the sauna in the main station, turn it all the way up. So like, plus 200 or whatever. Hang out there for a while, get our core temperatures up, and then go run outside in only a pair of boots. So it's not, we don't run, we walk briskly with purpose to the geographic South Pole.
Which is how far?
You've checked that box. Let's say it moves every year, actually a little bit, but it's about 100 meters.
Okay.
So, yeah, it's a decent walk. You can see it out the window, like kind of far away.
So, what does 100 degree below zero air feel like? I mean, I grew up in Minnesota. I know what like 50 below feels like.
Yeah.
I can't even imagine. Just burning? Is it just it's burning or what?
It is kind of a burning. Yeah. So for the first like 30 seconds to a minute, it feels fantastic if you just come out of the sauna. Just like a cool breeze, right? And then suddenly, you start to have a little bit of trouble breathing, and if you sweat, your sweat will freeze immediately. Hence, don't run when you're out there in that temperature. But it's I think of it more as like how long can you stand to be out in that temperature, and not that it feels. Eventually, minus 80 will also feel as painful as minus 100 if you're out there long enough.
Okay.
You know what I mean?
In the sense that it will eventually kill you.
Well, yeah. But yeah, it is kind of like a stinging, you definitely feel it in your lungs if you're breathing in that cold air, and you got to, cover your face pretty well, keep your extremities covered so that frostbite can be basically instantaneous.
So I know there's a name for the people who have done this 200 degree to minus 100 degree feat. What do you call it?
It's called the 300 Club.
How many members does this club have?
Oh, man. So I am the 1621st unique person to winter at the South Pole.
But not all of them are members of the 300 Club.
Right. So many are. So
okay, all right.
Be generous and say like 1,200.
Okay.
I'm going to use this opportunity to plug a friend of mine who's got a good YouTube channel that shows some of this stuff. Joe Spins the Globe. He's got a video of me walking from the station to the out to the telescope, and it's a walk that I did nearly every day when I was there for the winter. It's just 16 minutes of my feet crunching on snow, and that's kind of fun to watch for people who like that kind of thing.
So maybe we can open some questions up to kind of the both of you now. Just kind of a general question, but like just what are some of the examples of challenges that you face trying to do your experiments at places like the South Pole or underground at Snow Lab that physicists might not normally face elsewhere?
You want me to go first, Sasha?
Sure.
I've got one that I'm sure is true for both of us. Don't forget a tool. If you forget a tool, you're not doing the work that day, right? And I'm sure that's as true for walking between the buildings at pole as it is to going underground. What that results in is actually something that is very common at Snow Lab, and I would expect is true at pole as well, which is a very communal and collaborative scientific environment, where because there are multiple experiments working in the space, if you realize you forgot one length of screw that you just really need that day, you talk to everyone else down there, and everyone will go out of their way to try to help you because they know that next week it could be them.
Right.
And so there's a really awesome sort of camaraderie and collaborative culture that fosters that I think is really beautiful for science.
Yeah, absolutely. If you don't ship it there at the beginning of the season, chances are it won't arrive before the station closes for winter, and then you kind of have to make do with what you got. So we have a fully, decked out lab out there. So, if we have some emergency, fine precision work that we need to do, we can do that. We've got a machine shop, but for sure, we're definitely sharing resources there.
Do you get pretty good at improvising missing equipment?
Yeah, absolutely. Yeah. So I think am I allowed to talk about this on air?
That's the problem. I had the same thought. I have stories, but I shouldn't talk about them.
I assure you it's fine. Yeah, go ahead.
OSHA would disagree.
It's kind of like an airing dirty laundry thing. I don't know. I'll go with it because I'm pretty sure people know about this at this point. It's been like 6 years. So a few years ago, we had like a mechanical failure of the motors on the telescope, and that resulted in some damage to the camera inside the receiver cabin. So like the optical components of the telescope. And we had two wind rovers there, one of whom had seen the inside of this camera. And then we also had a really great machinist, Steele Diggles, which is a really great name. When I say camera, I'm actually talking about the detector technology that maybe Dan is reasonably familiar with. It's a cryogenic instrument. We use superconducting transition edge sensors, so some condensed matter physics, basically to get the sensitive elements of our camera to record that millimeter wave signal from the sky. So it's a big onion. We have to like open up the whole thing and pull out this camera. It was a whole process. The machinist worked magic basically to carefully remove this thing, fix it, and they had to re-glue some parts and reassemble some parts and salvage what they could and then reinstall it. And that whole process took, I want to say, like a few months, like 3 or 4 months. So it's a good chunk of their winter time. There's, obviously no planes in or out, and they had to make do with what they had to recover it. And they were able to get the instrument back on the sky in that amount of time. And we've since published results based on the data that we took after that happened, which is pretty awesome. Yeah. That's kind of like the biggest thing that we've had to do.
Challenge overcome.
Yeah. It's not like you can use duct tape and zip ties to fix it at that point.
But I imagine duct tape and zip ties get a lot of work down there, right?
Oh, absolutely. Probably the Spider telescope, the balloon payload I worked on before, is actually probably 50% duct tape and zip ties by construction because it's lightweight.
Yeah.
We have a different problem. Duct tape is very, very bad.
Why?
Radioactivity.
Oh, what's the radioactive component in duct tape?
It's more just that stuff sticks to it.
Oh.
So it kind of collects dust over time.
Okay.
It also leaves residue. And so we try to avoid duct tape. We're very on the zip tie train, though. Zip ties are underrated for science. There's a lot of applications of zip ties.
So just for concerned listeners, the kind of radioactivity Dan's talking about here is, again, not dangerous even remotely. It's that they're sensitive. Their experiment is so sensitive to trace levels of radioactivity that they need to worry about things that we would never need to worry about.
That's right. So for scale with something that you might be familiar with, a banana in our detector would absolutely destroy us, right? That would be so much radioactivity.
Because of the potassium, right?
Because of the potassium.
Which is radioactive,
exactly.
But not in a dangerous way.
But not in a dangerous way. And so that's, when I say radioactivity, we truly mean at a level that is irrelevant for people. but absolutely critical for us.
Do the scientists working in Snow Lab have to like watch their food consumption, like not eat bananas and things?
No. It would be very interesting if a scientist could turn themselves radioactive enough that if they stood next to a detector, it would be detected. But I'm not aware of a time that has happened.
Well, but if a banana is sufficiently radioactivity, then presumably a banana in my stomach would be too, right?
Well,
What's
part of the reason that isn't a problem is that all of the ultrasensitive detectors we have underground, so this is true for Pico, this is true for Domic, Sensei, all the others, have multiple layers of shielding. And so they're typically surrounded by a lot of lead and then a lot of water or plastic. And the purpose of that is, even though going underground removes a lot of the cosmic rays and backgrounds that you would have on the surface, you still have a lot of radioactivity in the rock around you. As I mentioned before, mine dust is quite radioactive from the levels that we care about. And so similarly to how you surround your detector with material to shield it from the rock, that material would shield it from a banana that you ate.
Gotcha. Sasha, I want to ask you a little bit about maybe some of the social or psychological challenges that might come up in putting 40 people in an extremely isolated environment without any sunlight for, I don't know, 6 or 8 months at a time. That must, I mean, like, I just can't imagine that would consistently go well. Am I right that that's as hard on people as I think? Yeah.
You're not wrong. So there's a couple different things that tend to come up. You know, one is kind of lack of sunlight. That's kind of the major one, right? So the sun sets and then the nighttime is really pretty, actually. So you get auroras happening almost daily. Especially there's this really fun cycle with like the moon is up for 2 weeks and then it's down and then it's just super dark and you can see all these auroras in the sky. And so that's kind of, you know, it's nice to go outside and look at them and like take pictures. But the darkness does get to people. And there's, I think it's called like T3 syndrome. There's actually physiological effects that have been sort of documented, and people, you know, you kind of get a little bit aloof, like some memory loss, some distance, and you know, you get the 1,000-yard stare kind of thing going. So, you know, I've seen that happen to a couple people at some level, but we usually take vitamin D supplements pretty regularly when we're down there, and that tends to help. And there's the nighttime, and there's also, like, to be perfectly honest with you, like boredom. You know, you run out of stuff to do because the station is only so big and you can only walk around it so much. But we have, you know, a craft room, we've got a music room, we've got a greenhouse, we've got a weight room, a big, you know, volleyball, basketball gym. We've got a bunch of movie rooms and video games. We have the largest Betamax collection in the Southern Hemisphere or something like that.
Betamax. Okay. That's very specific.
I have no idea if we still have a working Betamax player, but there it is. My winter, I think what worked really well was that we had kind of daily and weekly and monthly kind of activities to look forward to that helped pass the time. So, you know, we would have like particular movie nights. We watched a couple of like sci-fi movie series every weekend, and we'd make sure not to, you know, get ahead of ourselves. And then that's something you look forward to. Or we'd have a monthly like trivia night, burger bar thing, you know, or like, you know, cocktail hours or something like that, right, that we would plan. And like the major holidays in the winter are sunset, midwinter, and sunrise. So okay. March 22nd-ish, June 22nd-ish, and September 22nd-ish. And so we'd turn those into huge affairs, you know, big fancy meals, everybody get dressed up.
I'm trying to picture what being dressed up looks like in the pole. I don't imagine you bring tuxedos and gowns.
Oh yeah.
Oh
Some people bring, you know, okay, like formal dresses down. Yeah.
Okay. Yeah, I stand corrected.
I planned ahead and I brought a dress for every occasion. Just 'cause it's something fun to do.
All right.
Yeah.
And then
for sure.
Following up on this, like, how much contact do you have with the outside world there? I mean, can you make phone calls? Can you, I assume you have the internet to some extent or something? What's that like?
Yeah, so we have all of our internet access comes in over satellite. We have access to a couple different satellites, but you know, the upshot is that it's only a few hours a day that we have good coverage, and that that, window of time kind of shifts with sidereal time with the motion of the Earth around the sun. So it's, 4 minutes earlier every day. And let's say the good satellite hours it's about a 5-hour chunk. But yeah, it's pretty isolated. You kind of stop paying attention to the news at some level, or like stop paying attention to, events outside of South Pole, or they're kind of so far away that they don't really bother you too much.
That sounds kind of nice.
Oh yeah, it is actually kind of pleasant. And then on the, the back end, it's kind of shocking to then re-enter society and
Yeah.
So I wintered in 2021 and I left in December 2021. I was, kind of hoping I would skip most of COVID by staying at the South Pole for a year. And then 3 weeks after I got back, I got COVID. So it's kind of a shock to the system a little bit. But yeah, mostly the people I work with and live with, we all kind of knew that we were on the same boat, and so you kind of have to take everything in stride a little bit. Like, stuff does come up. People get squirrely with each other. Some people never quite get along. Right. And you kind of just have to, deal with it in one way or another and not let it get to a boiling point. And that takes a little bit of work.
So to close out, I was wondering for both of you, is working in these sorts of extreme locations something you actually enjoy, or is it just something you sort of brace for the sake of science?
I definitely enjoy it. It's really kind of rewarding to get to spend some time in one of these remote places that very, very few people get to go to, ever. I think it's really amazing that we're able to do this kind of large scale science in a place that's so remote.
Yeah, same for me. I absolutely love it. I think the work that I've done at Snow Lab in particular, underground, is some of the most rewarding and satisfying work I've done in my career. And I think the people that I met there and just the environment of working underground, it's one of the best places I've ever worked. I absolutely love it. And there's so many, like Sasha said, there's so many little unique experiences that you get out of that give you this just incredible sense of perspective that's very hard to convey. I mean, the two big ones for me, and I'm sure Sasha could list a lot of them, is just being out in a mine, before you get to the lab, everyone sort of walks at a different pace. And so it's possible that on that 2-kilometer walk, you can be, kind of alone for a little bit. And there is a satisfaction to just turning off your cap light for a minute and sitting in total darkness, a mile under the earth. And it's surreal. I mean, I can't even describe that type of feeling and isolation and sort of just perspective. It's absolutely incredible. The other thing is it gives you a real respect for the planet. I think Sasha might say something similar. I'm very curious, but one of the things that is true for being underground is rock isn't constant. Rock moves. And most people don't think about that. And in particular, if you're in an active mine, it moves a lot more. And so all the time you're down there, you're hearing little noises around the lab because the rock around the lab is shifting. And it's shifting against other rocks. So you have snaps, you have bursts. In the lab, we call them rock bursts, but it's just sort of a constant background noise that you get very accustomed to, but it's literally the sound of the earth moving and adjusting. And that is very cool to think about.
That's awesome. Yeah.
I'm curious, Sasha, what those things would be for Pole, because I'm sure there's some things that it's just you can't even begin to describe the experience of unless you were there. And
yeah, I mean, it's incredibly quiet at the South Pole. There's, especially in the winter when there aren't any vehicles moving around outside. When, you walk out, it's 1 kilometer from the main station out to the telescope. You can walk pretty much in any direction if you want to, as long as you have your wits about you and a light. But it's super quiet, and there's nothing on the horizon. It's a desert, right? So there's no skyline or ridgeline or mountains or anything to look at. It's just you and the stars, or you and the sun, or whatever it is, the moon. And so, yeah, you kind of feel like a little speck out in the universe. I think one of the clearest views I've seen of the Milky Way is from there at night. You can make out all of these features in the Milky Way, all the dust and stuff, and like the large and small Magellanic clouds and stuff. So that's really kind of awe-inspiring a little bit.
I think there's something quite poetic about the fact that both of you went to these extreme places on Earth to study the universe, to study the Big Bang, to study the nature of dark matter, and you found yourself being struck by senses of awe associated with our own planet. Like maybe looking towards the universe took you to somewhere that, made you appreciate something magical about our own backyard.
Why This Universe is brought to you by the University of Chicago Podcast Network. It's edited and produced by me, Shalma Wegsman, and my co-host is Dan Hooper, a professor of astrophysics at the University of Chicago and Fermilab. If you like our show and you want to support us even more, you can find us on Patreon. There you can access ad-free episodes of the show, as well as exclusive Ask Us Anything episodes where you get to ask Dan and I direct questions about physics or anything else. So if you are curious about that, you can find it at patreon.com/whythisuniverse. Thank you so much for listening and for your support.